Something impossible has just unfolded in the depths of space. An event so extraordinary that governments and scientists alike are scrambling to keep the public calm. A 33 billion-ton interstellar visitor, now officially named 3I Atlas, has been caught performing behaviors that defy the very laws of physics as we understand them. And believe me, this is only the beginning. In just the past week, humanity has witnessed a cascade of breakthroughs and anomalies that feel almost too incredible to be real. A disease once considered an inescapable death sentence has been cured with a single injection delivered directly into the brain. NASA scientists have uncovered what they claim is the strongest evidence of life on Mars ever found. Astronomers have discovered black holes that shouldn't even exist according to our current models of the universe. And in case that wasn't enough, your smartphone has quietly begun tracking your mental health in ways most people don't even realize. We are talking about quantum echoes that may be coming from another dimension. Contact lenses that grant near superhuman vision are no longer science fiction, but early-stage reality. Geneticists have just revealed that fragments of ancient viral DNA imprinted into our genome millions of years ago may still be influencing how we think and behave today. And as if the universe wanted to raise the stakes, the Sun itself has unleashed a massive plasma blast aimed directly at our interstellar visitor, a cosmic act that some researchers are half-jokingly referring to as a shot across the bow. Right now, Nobel Prize-winning physicists are warning that this could be reconnaissance, a probe sent by someone or something from beyond our solar system. We are seeing internet speeds leap forward with the dawn of true 6G networks, pain-blocking treatments that might eliminate suffering entirely, and technologies that seem pulled from the pages of speculative fiction. This is no longer just science news. This feels like reality itself is beginning to unravel, forcing us to confront a future that is arriving faster than we ever expected. Buckle up, because what I'm about to share with you may make you question whether we are still living in the same world we woke up in just a week ago. If you're ready to dive deep into the data, witness the most profound discoveries of the decade, and see why scientists are losing sleep over what they've just found. Stay with me, because this story is only getting stranger. Chapter 1. The Arrival of the Impossible on July 1, 2025. The Atlas Telescope Array in Chile made a detection that sent shockwaves through the global astronomy community, moving through the solar system at a blistering 37,000 miles per hour. Fast enough to travel from Earth to the Moon in less than 2 hours, was an object that would soon receive its official designation, 3I Atlas. The 3I stands for Third Interstellar Object Ever, confirmed by human observation following the mysterious Oumuamua in 2017 and Comet 2I Borisov in 2019. But 3I Atlas is not just another member of the same category. It is something far more massive, far stranger, and far more disruptive to our understanding of how the cosmos works. At first, astronomers assumed it was merely another comet wandering between the stars. Yes, its speed and trajectory were unusual, but still within the boundaries of what physics could explain. That illusion shattered as the data poured in from observatories worldwide. The first red flag was its brightness. Most comets this far from the Sun are essentially invisible, no more than dark rocks coasting silently through space. They only flare into visibility when the Sun's heat warms their surface, causing their ices to sublimate and form the glowing coma and tail we associate with classic comets. But 3I Atlas was glowing when it was first spotted, at a distance where it should have been completely dark. It appeared to be shining with its own internal energy source, as though some hidden engine were illuminating it from within. Then came the size estimates. Using the Hubble Space Telescope, astronomers calculated that the nucleus of 3I Atlas is somewhere between 1,400 feet and 3.5 miles across, making it potentially larger than 99% of all comets ever observed. This thing isn't just big, it is colossal. And then just days ago, a research team led by Harvard astrophysicist Avi Loeb published a paper that detonated like a bombshell in the astronomical community. By tracking the object's trajectory, using over 4,000 separate observations from 227 observatories worldwide, they determined that this cosmic intruder has an estimated mass of 33 billion tons. To put that in perspective, That is the equivalent of 66 billion elephants. It's roughly 1,000 times the mass of the Empire State Building. It is, in every sense of the word, a mountain hurtling through space. But here's where it gets truly bizarre. An object this massive shouldn't even be here. According to our current understanding of planetary system formation, objects this big require extraordinary gravitational energy to be ejected into interstellar space. Ejecting something this large would normally require a catastrophic series of events. Multiple giant planets flinging it around like a cosmic slingshot until it escaped its star's gravity. Even then, the probabilities are vanishingly small. Loeb and his colleagues argue that statistically, we should have discovered hundreds of thousands of smaller interstellar objects before ever stumbling upon a behemoth like this one. The fact that we've now seen 3 interstellar objects, and one of them is this massive, is a glaring hint that something about our understanding of the universe is wrong, or that something deliberate is happening. Chapter 2. The trajectory. That shouldn't exist. Another puzzle came when researchers analyzed its trajectory. Normally, comets experience slight shifts in their path as their ices sublimate, producing tiny jets of gas that act like thrusters. This non-gravitational acceleration is one of the key signatures that allows us to tell a comet apart from an asteroid. But 3I Atlas is behaving differently. Despite showing clear evidence of outgassing, it has a visible coma and tail. Its trajectory is almost perfectly gravitational. It's as if the jets have no effect at all, as though the object is so heavy that the thrust is meaningless. This is where its enormous mass becomes important. If it truly weighs 33 billion tons, then yes, it would take an immense force to alter its path. But this just deepens the mystery. How did something this massive get ejected from its parent star system in the first place? Chapter 3. The Chemical Enigma. The James Webb Space Telescope delivered yet another shock. Spectral analysis of 3I Atlas's coma revealed a carbon dioxide to water ice ratio of 8.1, one of the highest ever recorded. Most comets in our solar system are made mostly of water ice, with carbon dioxide and other frozen gases present only in small amounts. But this object appears to be dominated by carbon dioxide, dry ice. This means it likely formed in a very different environment, possibly in the frigid outer reaches of its parent system or under unusual radiation conditions that preserved its CO2 while removing other volatile compounds. Dr. Jacqueline McClary of Northeastern University commented, "This isn't just a comet from another system, it's a chemical time capsule. Its composition suggests that the place it formed may have been radically different from anything we know in our own solar system." Even more intriguing, 3I Atlas was glowing and actively venting material long before it reached the inner solar system. That means it has likely been releasing gas steadily during its entire interstellar journey, perhaps for millions of years. Chapter 4. The Sun Fires. Back just. When scientists thought the situation couldn't get any stranger, the Sun itself appeared to respond. In an event now dubbed the solar bombardment, our star unleashed a powerful coronal mass ejection, CME, precisely along the path of 3I Atlas. While CMEs are common, the timing and direction of this one have raised eyebrows. The blast appeared almost perfectly aimed at the object, a cosmic coincidence so striking that some researchers have suggested it might be worth asking whether 3I Atlas somehow triggered it. For now, the object continues its silent glide toward its closest approach, after which it will slip behind the Sun for 2 months, vanishing from view and leaving astronomers blind to whatever happens next. If this is simply a comet, then it is the most extraordinary comet in history. If it's something else, a probe, a relic, a messenger, then we may be standing at the threshold of one of the most profound discoveries humanity has ever made. Whatever happens, one thing is certain: the universe just reminded us that it still has secrets, and some of them may be heading straight for us. Chapter 5. The Solar Barrage and the Vanishing Act. Earlier this week, our star made its move. The Sun unleashed a massive coronal mass ejection, CME, a billion-ton bubble of charged plasma and tangled magnetic fields, straight toward our interstellar visitor. For those unfamiliar, Coronal mass ejections are among the most violent phenomena in the solar system. They can hurl billions of tons of solar matter into space at speeds exceeding 1,000,000 miles per hour. When aimed at Earth, they can fry satellite electronics, disable power grids, and produce auroras that ripple as far south as the tropics. When they hit comets, the results are usually spectacular. The intense radiation blasts away the outer layers, causing sudden brightening followed by a temporary loss of the comet's tail. But 3I Atlas didn't behave like any normal comet. NASA's space weather models predicted the CME would collide with the object on September 25th, and enthusiasts around the world tuned in to watch the event. What they witnessed was nothing short of astonishing. According to spaceweather.com, which has been tracking the interaction in near real time, the CME slammed into 3I Atlas with the force of a cosmic tsunami, and the object simply shrugged it off. Instead of flaring dramatically or losing its tail, 3I's Atlas remained eerily stable, its brightness unchanged, its trajectory unaltered. For comparison, when comets like Encke or Lovejoy have been hit by CMEs, their tails have been ripped apart in dazzling, chaotic displays. Here, there was nothing: no violent shedding, no sudden fragmentation, no loss of cohesion. This almost stoic stability is yet more evidence for the object's extraordinary mass. A normal comet would have been violently disrupted by such a blast. The fact that 3I Atlas barely reacted suggests that its gravitational self-binding is powerful enough to hold it together even under direct assault. From one of the most energetic events our Sun can produce, Dr. Martin Connors, a space physicist who has studied comet CME interactions for decades, called the event a once-in-a-lifetime laboratory experiment. We are essentially watching a billion-year-old visitor from another star system get slammed by one of the most powerful space weather events our Sun can generate, Connors said. And instead of crumbling, it holds together like a fortress. That's telling us something very important about its internal structure. Chapter 6. The Missing Months has. If things weren't strange enough, the universe has just introduced a frustrating twist. We are about to lose sight of 3I Atlas at the very moment it becomes most interesting. By early October, the object will slip behind the Sun from Earth's point of view, entering a period known as solar conjunction. For roughly 2 months, ground-based telescopes will be unable to observe it directly. Normally, this isn't a big deal. Dozens of solar system objects pass behind the Sun every year. But in this case, the timing could not be more inconvenient. While hidden from our view, 3I Atlas will reach perihelion, its closest approach to the Sun, on October 30th. Perihelion is when comets are at their most active, venting gas and dust in massive outbursts that reveal their true nature. This is the moment when astronomers usually learn the most about a comet's composition, activity cycles, and internal structure. But this time, the entire show will play out behind the Sun, where we cannot watch. For many scientists, this is simply bad luck. But for others, it has raised uncomfortable questions. The object's closest solar approach happening exactly when Earth is blind to it feels, to some, like one coincidence too many. When 3I Atlas finally emerges from conjunction in late November or early December, it may look dramatically different. The Sun's relentless radiation will have stripped away much of its icy surface, potentially exposing its rocky or metallic core. By then, however, it will be receding from the Sun, growing dimmer and more difficult to study. With every passing day, the European Space Agency is attempting to make the most of this frustrating situation by coordinating a campaign. Using assets far from Earth, its Mars orbiters and the Jupiter-bound JUICE spacecraft have been tasked with observing 3I Atlas during its hidden months, giving scientists at least some data from the critical perihelion period. Still, these instruments are limited compared to what Earth's massive observatories could achieve. Chapter 7. The Path That Raises Questions, Perhaps. The most unsettling piece of the puzzle is 3I Atlas's trajectory. Most interstellar objects follow sharply hyperbolic paths, whipping through the solar system in a quick flyby before vanishing forever into interstellar space. Their orbits are entirely chaotic, determined by random gravitational encounters in their home systems and the pull of our Sun. But 3I Atlas's route feels strangely optimized. It entered the solar system from the direction of Sagittarius, on a path that takes it remarkably close to several key planets, close enough for detailed observation, but far enough to pose no threat. On October 3rd, it will pass within just 30 million kilometers of Mars, offering spacecraft orbiting the red planet a once-in-history opportunity to examine an interstellar visitor up close. Then, weeks later, it makes a near-perfectly timed perihelion passage, just as its activity should peak. Some researchers have quietly pointed out how statistically unusual this path is. The geometry allows for extended observation periods, multiple close planetary flybys, and long windows for data collection. Had it arrived just a few months earlier or later, Earth-based observatories could have tracked it continuously for over a year, gathering unprecedented data. It's almost as if this object is giving us the best possible chance to study it. Chapter 8. The Scientific Reckoning Within the Global Astronomical Community. The mood is a mixture of awe, excitement, and unease. On one hand, Three-Eyed Atlas is an unparalleled scientific opportunity, a chance to study primordial material from another star system, to test our models of planetary formation, and perhaps even to learn about environments radically different from our own. On the other hand, its mass, its composition, its stability, and its almost purposefully convenient trajectory are forcing scientists to confront questions that edge uncomfortably. Close to the territory of speculation, some researchers insist that we are simply witnessing a rare but natural event, a statistical outlier that just happens to be spectacular. Others are not so sure. Could this object be more than a comet? Could it be a fragment of an alien world, a derelict interstellar craft, or even, as a few bold voices have suggested, an intentional probe? For now, the debate continues. What's certain is that Three-Eyed Atlas has already rewritten the textbooks, and when it emerges from behind the sun in a few months, it may force us to rewrite them again. On one hand, the anomalous behavior of this interstellar object has given scientists an unprecedented opportunity to deepen their understanding of how planetary systems form and evolve. On the other hand, its unusual properties are challenging some of the most fundamental assumptions about the architecture of planetary systems and the dynamics of interstellar objects. Dr. Robert Warwick, who was part of the original team that discovered Oumuamua, described Three-Eyed Atlas as the most scientifically important interstellar object we've ever detected. According to him, the combination of its immense mass, its peculiar trajectory, and its mysterious composition makes it a veritable treasure chest of information about how worlds are born, how star systems develop over billions of years, and what sort of material is exchanged between them. To researchers like Warwick, Three-Eyed Atlas is nothing less than a once-in-a-lifetime natural experiment, a rare opportunity to watch an uninvited traveler from the stars as it briefly crosses our cosmic backyard. Not everyone, however, shares that unbridled enthusiasm. Many scientists are urging caution, arguing that it would be unwise to overinterpret its strange behavior. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury, warned against leaping to sensational conclusions about the object's anomalous features. Every interstellar object we've detected so far has been unique in its own way, she explained. We simply don't have enough examples to know what's normal and what's unusual for visitors from other star systems. Bannister's perspective reflects a broader caution within the planetary science community. Our sample size is still vanishingly small. Oumuamua and Borisov were the first two confirmed interstellar visitors we had ever observed, and now Three-Eyed Atlas is only the third. 3 data points are not enough to draw sweeping generalizations about the population as a whole. The debate has grown even more complex with the participation of controversial figures willing to float unconventional hypotheses about what we may be witnessing. Among the most prominent is Dr. Avi Loeb, whose outspoken willingness to consider extraordinary explanations has sharply divided the scientific community. Some colleagues applaud his boldness, praising him for asking the big questions that others are afraid to voice. Others worry that speculation about alien technology risks distracting from the very real, very serious scientific questions raised by Three-Eyed Atlas's motion and composition. Regardless of which side one takes, it is clear that this object has become a flashpoint, a mirror reflecting deeper disagreements about how science should be conducted in the era of rapid data collection, viral headlines, and social media-fueled speculation. Meanwhile, the clock is ticking. 3i Atlas is rapidly approaching solar in conjunction, the point at which it will pass behind the Sun from our perspective, and this means a critical 2-month window where no telescope on Earth will be able to observe it directly. For astronomers, this feels like a race against time. Every instrument capable of tracking it is working overtime, gathering as much data as possible before the object vanishes into the Sun's glare. The stakes are high. This may be our last chance to measure its size precisely, analyze its spectrum, and refine our models of its trajectory before its behavior becomes even harder to study. When it finally emerges from conjunction in December, it may look very different. Its surface could have been altered by the Sun's intense heat, its activity level could increase or diminish, and its trajectory could be subtly changed. Scientists are eager to see what kind of transformation it undergoes and whether those changes hold clues to its origin. But even as the data comes in, speculation has begun to spiral in directions that would once have been confined to the fringes of science fiction. Welcome to Chapter 2, Alien Invasion or Cosmic Joke. This is the domain of the conspiracy theories, some of which are so provocative they have sparked heated academic feuds, prompted NASA to hold press briefings specifically to tamp down public anxiety, and ignited one of the fiercest debates in astrophysics since the battle over cold fusion in the 1980s. What makes this situation truly remarkable is that some of the most startling ideas about 3i Atlas are not coming from internet, forums, or UFO enthusiasts. They are being proposed by respected scientists, published in peer-reviewed journals, and supported by mathematically sound calculations that even skeptics grudgingly admit are difficult to dismiss. The most visible champion of this line of thinking is Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University. Loeb is no outsider. He is one of the most prolific astrophysicists of his generation, with over 800 published papers to his name, a long history of service on prestigious committees, and the distinction of having been the longest-serving chair of Harvard's astronomy department. For the past several months, Loeb has been making headlines with a provocative claim that 3 Atlas might not be a natural object at all, but rather an alien probe, a piece of technology sent intentionally or unintentionally into our solar system by an extraterrestrial civilization. Before you dismiss this as science fiction, Loeb insists, look at the evidence. His speculation is not a random flight of fancy, but is rooted in a detailed analysis of the object's trajectory, speed, and behavior, which he and his collaborators laid out in a paper that successfully passed peer review. The paper, titled "Is the Interstellar Object 3i Atlas Alien Technology?" He does not claim definitively that it is an extraterrestrial spacecraft. Rather, it argues that the hypothesis should be taken seriously, enough to warrant further study, that the idea is at least plausible given the data we have so far. Loeb's intellectual journey into what many consider scientific heresy began with a deceptively simple question. Why does 3i Atlas behave so differently from the other interstellar objects we have observed? The deeper he dug into the data, the more convinced he became that conventional explanations did not add up. For example, the object's trajectory is almost eerily aligned with the ecliptic plane, the same plane on which Earth and most of the planets orbit the Sun. The probability of such a near-perfect alignment occurring, purely by chance, Loeb calculated, is roughly 1 in 500. That alone is a statistical oddity, one that, in his view, demands some kind of explanation beyond coincidence. But the trajectory is only the beginning. Loeb points to a number of additional factors that, when considered together, create a picture that doesn't match our expectations for a natural comet or asteroid. Among them are the object's lack of a visible outgassing tail despite exhibiting non-gravitational acceleration, its unusual reflectivity, and the way it seems to be following a path that would be optimal for a gravitational assist maneuver, almost as if it were using the Sun's gravity deliberately, the way spacecraft do during carefully planned flybys. If 3i Atlas were a probe conducting reconnaissance of our solar system, Loeb and his co-authors Adam Hibbert and Adam Crow from the Initiative for Interstellar Studies argue, its current trajectory would be exactly what we would expect for such a mission. In his most recent analysis, Loeb pointed out that the ideal point for a so-called reverse solar Oberth maneuver, a maneuver that would allow a craft to slow down enough to become gravitationally bound to the Sun, would occur precisely at perihelion, the point of its closest approach to the Sun. Unfortunately, Perihelion is exactly when 3I Atlas will be hidden from view by the sun's blinding light, meaning we may never know whether it actually executes such a maneuver. This is what makes the coming months so crucial, Loeb wrote in a widely shared blog post. If we could observe what happens at perihelion, we might learn whether this is truly a natural object or something far more intriguing. In plain English, Loeb is suggesting that 3I Atlas could, in theory, change its velocity in a way that natural objects simply cannot, an unmistakable signature of artificial control. Whether such a change will be observed remains to be seen, but the mere possibility is enough to keep astronomers, skeptics, and dreamers alike glued to their telescopes. The next chapter of this story promises to be even more dramatic, with implications that could range from the merely fascinating to the potentially world-changing. If 3I Atlas wanted to secretly alter its trajectory and remain in our solar system permanently, the most strategic moment to do so would be when it is hidden from Earth's view, precisely when it passes behind the sun. In that position, the object would be completely invisible to ground-based and space-based telescopes, shielded by the sun's blinding glare. This would be the perfect opportunity to execute a gravitational assist maneuver, using the sun's massive gravitational field not to slingshot away at higher speed, as comets usually do, but to slow down just enough to enter a bound orbit around our star. Such a maneuver, if it were deliberate, would transform 3I Atlas from a temporary visitor into a permanent member of our solar system, and we would have no way of knowing until it emerged weeks later. Dr. Avi Loeb and his colleagues have argued that the timing is almost too perfect. 3I Atlas reaches its perihelion, the closest point to the sun in its orbit, on October 30th, exactly when it will be completely hidden from observation. If the object were to perform a trajectory-altering maneuver at that moment, we would not learn of the change until it reappears in December, and if its new trajectory pointed toward Earth, humanity might only have weeks or months to prepare. In their peer-reviewed paper, Loeb's team even speculated that if the object is under intelligent control, the possibility of a collision course cannot be dismissed outright, a scenario that might require unprecedented defensive measures for planetary protection. They have dubbed this alarming possibility the stealth technology theory. But Loeb is far from the only scientist exploring unconventional explanations for the mystery of 3I Atlas. A particularly imaginative and unsettling hypothesis has come from an independent researcher named Gabora, who has closely followed Loeb's work. Gabora proposes what he calls the stealth hybrid asteroid spacecraft hypothesis. His idea challenges the very way we think about alien technology. Instead of picturing shiny metallic flying saucers or massive starships bristling with antennas, Gabora suggests that advanced civilizations might take a subtler approach. According to this hypothesis, an intelligent species capable of interstellar travel might deliberately camouflage their probes to look like natural objects. They could terraform or hollow out asteroids and comets, install propulsion and guidance systems inside, and then launch them across interstellar space. To a primitive civilization like ours, such hybrid craft would appear to be nothing more than ordinary space rocks. The logic behind this idea is disturbingly compelling. Even humanity, with its relatively crude technology, is already planning missions to mine asteroids, build habitats inside them, and use them as natural shields against cosmic radiation. For a civilization thousands or millions of years ahead of us, such a feat would be trivial. This theory would also neatly explain many of the observed anomalies. The enormous mass of 3I Atlas could be accounted for by hidden internal structures. Its unusual brightness might be caused by reflective surfaces or concealed energy sources, rather than by normal cometary outgassing. Its near-perfect trajectory might not be the result of cosmic coincidence, but the product of careful course corrections executed over many years. Perhaps most chilling of all, a craft disguised as a comet could perform extensive reconnaissance of our solar system without arousing suspicion. Right now, humanity might be under observation, monitored with a precision we cannot even fathom, while we remain blissfully unaware that we are being studied like microbes on a petri dish. Adding more intrigue to the mystery is what some scientists are calling the nickel without iron anomaly. Spectroscopic analysis of 3I Atlas has revealed the presence of nickel in its composition, but oddly no detectable iron. This is a puzzling finding because, in natural cosmic objects, nickel and iron almost always appear together. They are forged in the same stellar processes and typically occur in roughly similar proportions. Finding nickel without iron is like finding salt without sodium, possible under certain rare conditions, but highly unusual. Dr. Loeb notes that in terrestrial engineering, nickel and iron are often deliberately separated to create specialized alloys. Nickel-based superalloys are prized in advanced aerospace engineering because they can withstand extreme heat and resist corrosion. If 3I Atlas were in fact an artificial construct, the presence of processed nickel would make perfect sense from an engineering standpoint. Of course, natural explanations cannot be ruled out. There could be exotic stellar processes or unique interactions with interstellar radiation that separate nickel from iron. But when viewed alongside the other anomalies, the trajectory alignment, the brightness, the timing, this detail adds yet another piece to a puzzle that seems to defy conventional explanations. Perhaps the most haunting aspect of the debate is what some have called the timing conspiracy. Based on its current speed and trajectory, Loeb's team has calculated that 3I Atlas would have entered the outer reaches of our solar system around 8,000 years ago. This date is not arbitrary. Roughly 8,000 years ago marks the dawn of recorded human history. It was the period when agriculture flourished, permanent settlements grew into the first cities, and writing systems began to emerge. Think about what was happening on Earth 8,000 years ago, Loeb mused. Humans were building the foundations of civilization. If an extraterrestrial intelligence were monitoring the galaxy for signs of technological progress, this is exactly when Earth would have begun to stand out. In other words, if 3I Atlas were indeed an alien probe, it might have been dispatched around the time humans first started leaving permanent marks on the planet, cave paintings, temples, and early texts, and has spent millennia traveling through interstellar space to arrive just as humanity begins its own tentative steps toward space exploration. The chilling implication is that we might be under long-term surveillance, and this particular visitor could be here to check on our progress. Even more provocative is the possibility that its timing was designed to coincide with our technological maturity. The very system that discovered it, the Asteroid Terrestrial Impact Last Alert System, ATLAS, only became operational in the last decade. Could this be a deliberate choice by an intelligence that wanted to be detected, but only after humanity had the capacity to study it, yet not enough to interfere with its mission? Loeb's collaborator, Omri, has gone even further by proposing what he calls the decoy theory. According to this idea, 3I Atlas might not be the main event at all, but a diversion. By creating an object with just enough anomalies to guarantee that it would capture our attention, advanced observers might be luring us into focusing all our instruments and intellectual energy on this one object, while the real mission, perhaps involving smaller and stealthier probes, unfolds somewhere else in the solar system undetected. To test this hypothesis, Loeb has coordinated with the Galileo Project, a private research effort dedicated to investigating unidentified, anomalous phenomena, to monitor the sky for increased WAP activity during 3I Atlas's perihelion passage. The project's 3 observatories in Massachusetts, Pennsylvania, and Nevada will be on high alert during late October and early November. Not surprisingly, these theories have sparked what many are calling an academic civil war. Critics have not been shy in their rebuttals. Dr. Steve Desch of Arizona State University published a scathing critique of Loeb's analysis, accusing him of sloppy reasoning and even mocking his conclusions in a widely shared graded assignment posted online. "Are you sure you're ready for a class on comets?" Desch quipped, implying that Loeb had overlooked basic cometary science. Other astronomers have voiced concern that sensational claims about alien spacecraft risk undermining public trust in the scientific process. "Extraordinary claims require extraordinary evidence," said Dr. Alan Fitzsimmons of Queen's University, Belfast. "And right now we simply don't have that evidence." Still, Loeb has defenders. Dr. Sarah Seeger of MIT, while not endorsing the alien hypothesis, praised Loeb's courage in asking unconventional questions. "Science advances by challenging assumptions," she noted, "even if Loeb is wrong. Exploring these ideas helps sharpen our understanding of what is possible." The controversy grew so intense that NASA felt compelled to step into the fray with a public statement. Dr. Tom Statler, NASA's lead scientist for solar system small bodies, flatly rejected the alien spacecraft idea. "It looks like a comet. It behaves like a comet. All the data we have points to it being a comet." he said at a press briefing, systematically addressing each anomaly cited by Loeb's team. According to Stadler, its unusual brightness can be explained by a surface rich in carbon dioxide ice. Its trajectory is consistent with a very massive object under normal gravitational influence, and its chemical signature is unusual but not unprecedented. Even so, NASA's unusually strong response has left some observers wondering whether the agency is overcompensating, perhaps out of fear of public panic, or perhaps because there is more to the story than they are letting on. The truth, at least for now, remains hidden behind the sun, waiting to reveal itself when 3I Atlas reemerges. The scientific debate surrounding 3I Atlas has become even more complicated, with the rise of fabricated claims that have gone viral across social media platforms. One of the most prominent false stories is a widely shared narrative claiming that Elon Musk confirmed that 3I Atlas is an alien spacecraft during a SpaceX press briefing. This story, which quickly spread across YouTube, Facebook, and countless reaction channels, quoted Musk as supposedly saying, "This is not just another comet. 3I Atlas is not natural. It's an alien spacecraft, and it's coming toward Earth." Of course, Musk never made such a statement. The viral claim is entirely fabricated, cobbled together from AI-generated fake quotes and recycled press images to craft a compelling but entirely false story. The hoax has been so effective that it has attracted millions of views and inspired countless content creators to produce speculative videos, many of them either unaware of the fabrication or knowingly using it to generate clicks. The result has been a digital storm of misinformation that is making it even harder for legitimate scientists to discuss the real, data-driven anomalies surrounding 3I Atlas. When serious researchers raise legitimate questions about the object's unusual trajectory or composition, they risk being dismissed as conspiracy theorists or grouped together with hoaxers. This blending of credible science with sensational fake news has created a credibility crisis, where public perception is easily swayed by viral content rather than peer-reviewed research. The pedagogical exercise. Defense faced with a wave of criticism from his peers. Dr. Avi Loeb, the Harvard astrophysicist at the center of the alien hypothesis controversy, has softened some of his strongest public claims. In recent interviews, he has framed his alien probe hypothesis as more of a pedagogical exercise, suggesting that its primary purpose was to encourage scientific debate and challenge conventional thinking rather than present a definitive conclusion. Loeb has emphasized that he finds it intellectually stimulating to consider unconventional possibilities, regardless of their likelihood of being true. This rhetorical pivot has satisfied some members of the scientific community who view it as a necessary clarification, but it has also frustrated others. Critics argue that Loeb continues to promote these ideas in public forums, podcasts, and media interviews, which stirs public excitement, while he simultaneously downplays their seriousness in academic circles. This dual strategy, some say, creates confusion and risks undermining public trust in science. Dr. Catherine Fess, a theoretical astrophysicist at the University of Texas, expressed this frustration clearly. The problem isn't that Dr. Loeb is asking these questions, it's how he's asking them. Science requires rigorous methodology and careful interpretation of data. Speculation can be valuable, but it must be clearly identified as speculation so that the public understands where the data ends and where the theory begins. For his part, Loeb argues that the scientific community has grown too conservative, too unwilling to challenge entrenched paradigms. Science is supposed to be about following the evidence wherever it leads, he contends. If we refuse to consider unconventional explanations for unconventional data, then we're not truly doing science. We're just protecting the status quo. The October test. The moment of truth. As 3I Atlas moves closer to its solar conjunction, a period when it passes behind the Sun from Earth's perspective, the alien spacecraft hypothesis faces its ultimate test. If the object is entirely natural, then when it re-emerges from behind the Sun in December, it should appear exactly where conventional gravitational calculations predict it will be. Its speed, trajectory, and brightness should all match models based on known physical laws. However, if there is any significant deviation, even a slight shift in trajectory that cannot be explained by gravitational interactions, radiation pressure, or outgassing, It would be a signal that something truly extraordinary is at play. Such a deviation would be the strongest evidence yet of a non-natural, potentially artificial influence on the object's motion. The stakes are enormous. A trajectory shift could change 3I Atlas from a fascinating scientific curiosity into the most important discovery in human history, evidence that intelligent technology exists elsewhere in the universe. Conversely, a perfect match with predicted natural motion would deal a severe blow to the alien probe hypothesis, pushing the conversation back toward more conventional explanations. Dr. Loeb and his collaborators have already calculated the precise location where 3I Atlas should appear if it behaves as a natural object. They are working with observatories around the world to ensure that telescopes are ready to catch its first glimpse after solar conjunction, giving humanity an unprecedented chance to confirm or refute the alien hypothesis. December will tell us whether we are witnessing the most unusual natural object ever discovered, Loeb stated, or whether we must seriously consider that we are not alone in the universe. But even as astronomers prepare for this decisive moment, other scientific breakthroughs are shaking humanity's understanding of reality in ways that may be just as profound. Chapter 3. Death Sentence Reversed. The Huntington's Gene. Therapy Miracle. While astronomers watch the skies, medical researchers have just achieved something that might change life on Earth forever. In what could be the most important medical breakthrough of the decade, scientists have developed a gene therapy that effectively halts the progression of Huntington's disease, a cruel, inherited neurological disorder often described as a genetic death sentence. Until this week, a person who inherited the defective HTT gene had no options. Their life would inevitably be marked by a slow decline as their body lost control, their mind deteriorated, and their personality was gradually erased. All while they remained painfully aware of what was happening. There was no treatment to slow the progression, no cure, and no escape from the disease's relentless march toward death. That changed on September 24, 2025, when researchers announced that their experimental gene therapy had reduced the progression of Huntington's disease by an astonishing 75%. This was not a marginal improvement or a small delay. It was a dramatic slowing of the disease that effectively grants patients decades of additional, functional life. Understanding the enemy Huntington's disease is unlike cancer, which attacks from outside, or diabetes, which can often be managed with medication and lifestyle changes. Huntington's is coded into a patient's very DNA, a ticking genetic time bomb that usually detonates in middle age. The disorder is caused by a mutation in the HTT gene, which produces a defective version of the protein huntingtin. Instead of supporting healthy brain function, the mutant protein is toxic, slowly killing neurons in key brain regions. Because Huntington's follows the unforgiving mathematics of dominant inheritance, a child of an affected parent has a 50% chance of inheriting the mutation. There is no partial inheritance, no carriers who remain healthy. Either you have the mutation or you don't. For those who do, symptoms typically begin between the ages of 30 and 50, often at the height of their careers and family lives. The disease begins subtly, small changes in mood, minor coordination issues, but it soon escalates into uncontrollable jerky movements known as chorea, cognitive decline, and profound personality changes. Over the next 10 to 30 years, the disease robs patients of their independence, their ability to speak, to care for themselves, and eventually even their sense of identity. Dr. Ed Wild, the principal investigator of the groundbreaking clinical trial at University College London, summed up the disease's cruelty. Huntington's doesn't just kill patients, it erases them. The gene therapy revolution. The breakthrough treatment, called AMT-130, represents a new frontier in medicine. Developed by the gene therapy company Unicurie, AMT-130 doesn't just treat symptoms, it targets the root cause of the disease at the genetic level. Rather than attempting to repair the faulty HTT gene, which would be technically complex, AMT-130 uses a clever workaround. It delivers instructions for a microRNA molecule that silences the defective gene, preventing it from producing the toxic protein altogether. This is achieved by packaging the microRNA instructions into a harmless adeno-associated virus, AAV, and injecting it directly into the patient's brain using precision, Neurosurgery, think of it like sending a microscopic cease and desist order to every neuron, instructing them to stop manufacturing the harmful protein that drives the disease. Results that stunned the world. The trial followed 29 early-stage patients over 3 years. 17 received a high dose of AMT-130, 12 received a lower dose, and their results were compared against a massive natural history dataset of untreated patients. The results were breathtaking. Patients who received the high dose not only slowed their decline by 75%, but some actually showed improvement on clinical measures. So that one patient who had previously been forced to retire because of disease symptoms was able to return to work, something previously considered impossible. Biological markers confirmed the clinical improvements. Levels of neurofilament light, NFL, a protein released when brain cells are damaged, dropped dramatically in treated patients, a strong sign that neuronal destruction had slowed or even stopped. Dr. Wild described the results with cautious optimism. For the first time, we are not just slowing Huntington's disease, we are seeing patients stabilize, and in some cases, improve. This could be the beginning of the end for this disease. In Huntington's disease, a devastating neurodegenerative disorder that slowly robs patients of their ability to think, move, and live independently. Scientists have long relied on a key biomarker to measure the relentless progression of the illness, neurofilament light chain, NFL levels. Under typical circumstances, NFL levels climb steadily, by roughly 20 to 30% over a period of 3 years. As increasing numbers of neurons succumb to the toxic effects of the mutant Huntington protein, this rise is a grim molecular signature, a biological reminder that the disease is continuing its destructive march through the brain. But something extraordinary, and perhaps unprecedented, has just been observed in patients treated with an experimental gene therapy called AMT-130. Instead of rising, NFL levels actually dropped. On average, patients saw an 8.2% decrease, a reversal of the biomarker that stunned researchers and suggested something remarkable was happening inside the brain. This was not just a slowing of neurodegeneration, not merely a delay of the inevitable. It appeared to be evidence that the therapy was actively protecting neurons and possibly even allowing damaged brain cells to recover. Dr. Joel Hurwitz of Stony Brook University, the lead author of the pivotal study, described this result as nothing short of groundbreaking. "We are not just stopping the disease," he explained. "We may be reversing some of the damage it has already caused." For a condition historically viewed as a one-way path toward decline and death, this statement represents a seismic shift in how scientists and clinicians think about treatment possibilities. Biomarker data is particularly important because it provides molecular-level validation of what clinicians observe in patients' behavior and function. Improvements in motor skills, mood, or cognitive abilities can be influenced by subjective assessment or even placebo effects, but changes at the cellular level, especially reductions in biomarkers of neuronal damage, are much harder to dispute. These results, therefore, give the clinical improvements seen in patients a much stronger scientific foundation. One of the greatest concerns whenever scientists attempt a brain-delivered gene therapy is safety. The human brain is arguably the most delicate and complex organ in existence, and directly introducing foreign genetic material into its tissue is not a trivial matter. The field of gene therapy itself has been scarred by tragedy, including severe immune reactions and patient deaths in early trials during the late 1990s and early 2000s, which temporarily shut down many programs worldwide. Researchers knew that if AMT-130 caused dangerous inflammation, off-target genetic effects, or irreversible harm, it could set back the field for years. Yet, to the surprise and relief of everyone involved, AMT-130 has demonstrated what can only be described as a remarkably clean safety profile. The most common adverse effects were those related to the neurosurgical procedure itself: headaches, mild disorientation, and small amounts of bleeding at the injection site. Importantly, these symptoms resolved completely within days or weeks, and no long-term complications were observed. Even more critically, there were no serious immune responses, no unexpected toxicities, and no evidence of the gene therapy interfering with unrelated cellular processes. Patients who received the treatment as far back as 3 years ago remain in good health today, with no indications of delayed side effects. This level of safety is especially impressive considering that this was a first-in-human trial. These were the very first individuals to ever receive AMT-130, and the researchers were still learning how best to administer the therapy, determine the correct dose, and monitor long-term effects. To achieve such robust efficacy with such minimal adverse events on the very first attempt suggests that the platform has enormous potential for refinement, improvement, and scaling to wider patient populations. The mechanism by which AMT-130 works is another fascinating part of this story. Rather than attempting the currently impossible task of repairing or replacing the mutant Huntington gene in every cell, the therapy uses an elegant technique known as gene silencing. It employs an adeno-associated viral vector to deliver DNA instructions that allow the patient's own cells to produce a small piece of genetic material called a microRNA. This microRNA is specifically designed to seek out and bind to the messenger RNA, mRNA, transcribed from the mutant Huntington gene. When the microRNA binds to this mRNA, it prevents the cellular machinery from using it as a template to create the toxic Huntington protein. In effect, the therapy turns off production of the protein that causes the disease, leaving normal cellular functions unaffected. The specificity of this approach is its greatest strength. The microRNA is tuned with exquisite precision to target only the harmful mRNA, dramatically reducing the risk of interfering with other essential proteins. Once delivered, the viral vector integrates into the DNA of brain cells, ensuring that the microRNA continues to be produced for years, perhaps decades, without the need for repeated dosing. The result could be lifelong protection after a single treatment session. Dr. Michael Treasy, a researcher involved in the trial, spoke to the long-term implications. We expect that patients who receive AMT-130 will continue to benefit for many years, possibly for the rest of their lives. This isn't a treatment that needs to be repeated every few months. It has the potential to be a one-time curative intervention. Just as importantly, these results have undergone one of the most rigorous processes in science: peer review. After the initial findings were released, the data was submitted to top-tier journals where independent experts in genetics, neurology, and molecular biology examined every detail. Peer review is designed to challenge assumptions, expose methodological flaws, and demand additional evidence where claims appear too strong. Studies that survive this process and are ultimately published in elite journals such as Nature are considered the gold standard in scientific reliability. That AMT-130's results were published there adds enormous credibility and assures the scientific community that the conclusions are not the product of wishful thinking or selective reporting. Behind all the graphs and molecular data, however, are real human beings whose lives have been touched, and in some cases, transformed by this treatment. The participants in this trial volunteered to undergo brain surgery with no guarantee of benefit, a decision that required immense courage. Dr. Ed Wild, one of the lead investigators, reflected on this point. Each data point represents a person who chose to take this leap of faith not only for their own sake, but for the sake of future generations. One patient's story in particular has resonated with clinicians. This individual had been forced to retire early due to the debilitating effects of Huntington's disease. After receiving AMT-130, not only did their symptoms stop worsening, but they improved enough to return to work, an outcome that many would have considered impossible just a few years ago. For Huntington's families who have endured generations of inevitable decline, such stories represent something they have not had in living memory: hope. Amy Gray, the president and CEO of the Huntington's Disease Society of America, summarized the mood. For the approximately 42,000 Americans and their families living with Huntington's disease, this is a truly transformative development. For decades, there have been no therapies to slow disease progression, only drugs to manage symptoms. This represents a fundamental change in what we can expect for the future. The success of this trial has now set the regulatory process in motion. Unicure, the company behind AMT-130, has announced plans to submit its data to the U.S. Food and Drug Administration in the first quarter of 2026, with similar filings expected for European regulators soon afterward. The therapy has already been granted both Breakthrough Therapy and Regenerative Medicine Advanced Therapy designations by the FDA, which allow for an expedited review process given the seriousness of the condition and the lack of existing treatments. If approved, AMT-130 would become the first therapy in history proven to slow or reverse the progression of Huntington's disease, representing a triumph, not just for the patients and families affected, but for the entire field of gene therapy. It would validate decades of research and pave the way for similar approaches to treat other inherited neurological disorders such as ALS, certain forms of dementia, and spinocerebellar ataxias. Challenges remain, of course. Manufacturing and delivering gene therapies is notoriously expensive, and experts predict the price per patient could exceed $2 million in line with other recently approved genetic medicines. But for families confronting Huntington's, a disease that robs loved ones of decades of life and independence, the potential of a one-time, possibly curative treatment makes the cost almost secondary. In the end, AMT-130 represents more than just a medical breakthrough. It symbolizes the culmination of years of scientific persistence, the courage of patients willing to take extraordinary risks, and the dawning of a new era in how we treat neurodegenerative disease. For the first time, Huntington's families have reason to believe that the future does not have to follow the grim trajectory of the past, and that hope, once a fragile dream, is rapidly becoming a scientific reality. As with any revolutionary therapy, the success of AMT-130 is forcing health systems around the world to confront difficult but necessary questions about access, cost, and equity. Health insurance companies, private payers, and national healthcare systems will have to determine how to cover a therapy that may cost over $2 million per patient, a staggering price tag by any standard, while recognizing that this is not just a temporary treatment but a potential one-time cure. The cost of inaction, however, is also immense. Huntington's disease places enormous emotional, financial, and societal burdens on families and healthcare systems. If AMT-130 can halt or reverse the disease process, it may ultimately save money over the patient's lifetime by preventing decades of progressive decline, institutional care, and loss of productivity. But the broader implications of this breakthrough go far beyond Huntington's disease itself. The microRNA-based gene silencing strategy used in AMT-130 could become a template for tackling a wide array of genetic disorders caused by toxic protein production. Conditions like amyotrophic lateral sclerosis, ALS, certain forms of Alzheimer's disease, muscular dystrophies, and other neurodegenerative syndromes may all be amenable to similar approaches. The success of AMT-130 proves not only that we can deliver gene therapy safely to the human brain, but that we can do so in a way that produces long-term benefit. Dr. David Rubenstein, professor of molecular neurogenetics at Cambridge University, summarized the excitement. This is a turning point not just for Huntington's disease, but for the entire field of neurogenetics. For decades, we've known that these diseases are caused by specific genetic defects, and we've dreamed about intervening at the molecular level. What AMT-130 shows us is that we finally have the tools to make those dreams a reality. For researchers, this success also represents validation of the entire gene therapy platform. For years, the field was haunted by early setbacks, immune reactions, delivery failures, and tragic trial outcomes that caused skepticism among scientists and regulators. But AMT-130 demonstrates that the technical obstacles can be overcome, that precise targeting is possible, and that the brain, once considered off-limits for large-scale gene modification, can indeed be treated safely and effectively. Looking ahead, the future of genetic medicine appears poised for rapid transformation. AMT-130 may be the first, but it will certainly not be the last therapy of its kind. Already, research teams are working on next-generation approaches that combine gene silencing with CRISPR-based editing, enhanced viral vectors for broader brain coverage, and multi-target strategies designed to address diseases with more complex genetic underpinnings. Within the next decade, it is entirely plausible that we will see genetic cures emerge for conditions like sickle cell anemia, Duchenne muscular dystrophy, and certain forms of blindness, and deafness that were once considered untreatable. The week of September 2025 may well be remembered as a historical inflection point, the moment when genetic medicine finally delivered on decades of promise. For the first time, having a faulty gene no longer means a guaranteed sentence of decline. It means being a candidate for precision therapy and potentially a cure. Humanity is stepping into a new era where our genetic destiny is no longer fixed. And remarkably, this theme of the impossible becoming possible is not limited to the realm of medicine. In the very same week that AMT-130 demonstrated the power to rewrite a patient's genetic fate, astronomers revealed a discovery that is rewriting the laws of physics themselves. Chapter 4. Physics laws don't apply here. The impossible black hole, just. When the world was marveling at the first therapy to reverse a fatal brain disease, the cosmos delivered an equally stunning revelation. Astronomers announced the discovery of a black hole so extreme, so beyond the limits of what theory says should be possible, that its existence is forcing scientists to revisit some of the most fundamental assumptions about the universe. Meet REX J032035, a supermassive black hole currently devouring matter at a rate 2.4 times higher than the theoretical maximum allowed by the laws of astrophysics. This isn't just a minor anomaly or a small discrepancy that can be explained away. This is a cosmic rule breaker, a gravitational monster that is apparently ignoring one of the bedrock principles of black hole growth, the Eddington limit. To appreciate how shocking this is, you have to understand what the Eddington limit represents. Named after British astrophysicist Sir Arthur Eddington, this limit defines the maximum rate at which matter can fall into a black hole before radiation pressure pushes back so strongly that it halts any further accretion. When matter spirals into a black hole, it forms a superheated accretion disk that radiates tremendous amounts of light and energy. At a certain point, that radiation becomes powerful enough to repel additional gas and dust, preventing the black hole from feeding any faster. The Eddington limit has been considered as fundamental to astrophysics as the speed of light is to relativity, a hard ceiling on how fast black holes can grow. And yet, REX J03 is not just nudging against that ceiling, it is smashing straight through it. Based on NASA's Chandra X-ray Observatory data, this black hole is consuming the equivalent of 300 to 3,000 solar masses per year, growing at a pace more than double what physics textbooks say should be possible. Imagine discovering a car traveling faster than light or a person with negative mass. That is the level of reality-bending strangeness this discovery represents. Its sheer size makes the puzzle even stranger. The black hole weighs roughly 1 billion times the mass of our Sun, already a monster by cosmic standards. For comparison, the supermassive black hole at the heart of our Milky Way galaxy is a relative lightweight at just 4 million solar masses. But what truly leaves scientists baffled is not just the size, but the timing. The light we see from REX J032035 began its journey to Earth 12.8 billion years ago, meaning we are observing it as it existed when the universe was just 920 million years old, less than 7% of its current age. In cosmology, this is known as the early supermassive black hole problem. To grow a billion solar mass black hole from the collapse of the first stars in such a short cosmic window would require uninterrupted, near maximum feeding for hundreds of millions of years. And even then, it should barely make the deadline. But REX J0335 isn't just meeting the limit, it's exceeding it by a factor of 2.4. Suggesting that either our models of early universe black hole growth are fundamentally flawed, or there are unknown mechanisms at work that allow black holes to bypass the Eddington limit entirely. Dr. Luca Ia of the Harvard-Smithsonian Center for Astrophysics, who led the discovery team, summed it up. The Eddington limit emerges directly from the physics of radiation and gravity. Finding an object that so flagrantly violates it forces us to ask whether we really understand these systems at all. This leads scientists to consider exotic explanations, including the possibility that REX J0335 did not form from the collapse of an ordinary star at all. One compelling idea is that it could be a primordial black hole, a theoretical object that might have formed directly from density fluctuations in the first moments after the Big Bang. Such objects could have been born with masses far larger than any stellar black hole, providing a head start that would make it possible for them to reach a billion solar masses so early in cosmic history. Dr. Alberto Moretti of INAF Osservatorio Astronomico di Brera put it bluntly. If REX J032035 really did start life as a primordial black hole, we are not just rewriting textbooks on black hole growth, we are rewriting the story of how structure formed in the universe itself. But even this exotic explanation doesn't fully account for the super Eddington growth rates we are observing. Primordial black holes might start out larger than those formed by collapsing stars, but they would still be governed by the same fundamental rules of physics. Radiation pressure should limit how quickly they can grow. As Dr. Priyam Vadarajan of Yale University, who has spent much of his career modeling early black hole formation, puts it, primordial black holes solve the time problem, but not the physics problem. We still need to explain how any black hole, regardless of its formation mechanism, can sustain growth rates that exceed what we've long considered a fundamental limit. Super Eddington accretion remains one of the biggest unsolved mysteries in astrophysics. The term super Eddington accretion has become a buzzword among astrophysicists, a shorthand for describing cosmic objects like Rex J0 32035 that seem to defy the rules. But to understand how this might be possible, we have to dive deeper into the complex physics of matter falling into black holes, a process that is far more complicated than the clean, idealized calculations in textbooks. The standard Eddington limit assumes a simple model: a black hole surrounded by a perfectly spherical cloud of infalling matter, with radiation pressure acting equally in all directions. In that model, there is a sharp point where the outward push of radiation exactly balances the inward pull of gravity, halting further accretion. But the real universe is not so symmetrical. In reality, matter falling into a black hole forms a rotating accretion disk, a turbulent magnetized maelstrom where gas, dust, and plasma spiral inward in a flattened, pancake-like structure. Dr. Mitchell Begelman of the University of Colorado, a leading expert on black hole accretion physics, explains why this matters. If radiation can escape preferentially along certain directions, for instance, along the rotation axis of the black hole, then the system can emit huge amounts of energy without choking off the inflow of matter from the sides. In such a beamed emission scenario, the black hole could continue to feed from the equatorial plane while releasing radiation through narrow jets. From our vantage point, the system could appear to be well above the Eddington limit, even though the actual radiation pressure acting against the inflow is much lower. This so-called beamed emission model is one of the most promising ways to explain sustained super Eddington growth. But it comes with caveats. It requires a finely tuned geometry, strong magnetic fields to collimate the radiation into jets, and a very stable accretion disk. Not every black hole could maintain these conditions for millions of years, yet the number of supermassive black holes we are now finding in the early universe suggests that whatever mechanism enables this growth was surprisingly common. This brings us to the second major hypothesis, the magnetic field solution. Magnetic fields are not just passive players in the accretion process. They can fundamentally change the behavior of matter near a black hole. Recent general relativistic magnetohydrodynamic (GRMHD) simulations, some of the most sophisticated computer models ever run, have shown that when magnetic fields become strong enough, they can create magnetically arrested disks, or MADS. In these scenarios, magnetic pressure becomes dominant and channels matter directly toward the event horizon along narrow funnels, reducing the effects of radiation pressure and allowing continued feeding. Dr. Alexander Jakovskoy of Northwestern University, who pioneered much of this research, describes the process. Strong magnetic fields can completely reorganize the flow of material around the black hole. Instead of a chaotic, turbulent disk, you get a highly structured inflow where matter is guided along magnetic field lines, like cars on a freeway. These magnetic funnels act as cosmic shortcuts, allowing gas to reach the black hole even when the overall luminosity of the system should be blowing matter away. The challenge here is that such magnetic fields must be extraordinarily strong and perfectly aligned, far stronger than any we have directly measured in astrophysical systems. Whether such conditions could persist long enough to grow billion solar mass black holes in under a billion years remains an open question. Some researchers are exploring even more exotic possibilities, including the idea that early black holes might have been fueled not just by ordinary matter, but by dark matter, the mysterious, invisible substance that makes up roughly 85% of all matter in the universe, but interacts only through gravity. In this scenario, supermassive black holes like Rex J032035 might have grown by consuming dark matter in the dense cores of the first galactic halos. because dark matter does not emit radiation. It would not be subject to the Eddington limit, allowing virtually unlimited growth until the local dark matter supply was depleted. Dr. Fabio Picucci of Harvard University has developed detailed models of this process, showing that if dark matter particles can be efficiently captured by a black hole's gravitational pull, they could provide an enormous reservoir of invisible fuel. In the early universe, dark matter would have been much more concentrated. A black hole sitting at the center of a dark matter halo could gorge itself on this invisible mass, growing rapidly before switching to gas accretion later in its life. This could neatly solve both the timing problem and the apparent violation of the Eddington limit, Picucci says, but this theory hinges on a major unknown: how efficiently black holes can capture dark matter. Standard models suggest dark matter is relatively collisionless and diffuse, making it difficult to funnel into the event horizon. New physics might be required to explain how such feeding could occur at the rates implied by observations, and the observational evidence is piling up. REX J032035 is no longer an isolated case. The James Webb Space Telescope, JWST, has been a game-changer in this area, giving astronomers the ability to see farther back in time than ever before, to the first few 100 million years after the Big Bang. What they are finding is a universe teeming with quasars, bright beacons powered by actively feeding black holes, far more numerous and massive than theoretical models predicted. Dr. Rebecca Ilsen of the University of Texas summarizes the new picture. Every time we point JWST at a patch of sky and look deeper, we find more of these early monsters. Some of them appear to have reached masses of hundreds of millions of suns in less than 500 million years. Our simulations just don't produce objects like that under the standard assumptions. Some of these black holes even appear to be growing at rates that are dozens of times above the Eddington limit, although follow-up observations often bring those numbers down. Even so, the pattern is clear. Rapid black hole growth was common in the early universe. Adding to the mystery are gravitational wave observations from LIGO, Virgo, and Kegra. These detectors have revealed a population of unexpectedly massive stellar black holes and mergers that produce larger remnants than anticipated. The most recent event, GW25014, involved the merger of two black holes around 33 solar masses each, forming a remnant of about 63 solar masses, consistent with Einstein's predictions, but notable for how frequently such massive systems seem to form. Dr. Maximiliano A. of Columbia University sees a common thread. Whether we're looking at quasars that break the Eddington limit or stellar black holes that are more massive than our models predict, we're seeing the same thing. Nature is finding ways to build bigger black holes faster than we thought possible. The implications for cosmology are profound. Early, fast-growing black holes could have been major drivers of cosmic reionization, the process that transformed the universe from an opaque fog of neutral hydrogen to the transparent, star-filled cosmos we see today. Their intense radiation could have heated and ionized their surroundings, influencing when and how the first galaxies formed. But accommodating these objects requires more than just tweaking a few parameters in our equations. It may force us to fundamentally revise our understanding of gravity, matter, and the behavior of space-time under extreme conditions. Some theorists are even exploring modifications to general relativity, or invoking extra dimensions to explain how such rapid growth could occur. As Dr. Marta Voluntari of the Institut d'Astrophysique de Paris puts it, we are in the middle of what can only be described as a theoretical crisis. Our best models cannot explain what we are observing. History tells us that such crises often precede breakthroughs. The last time we faced a crisis this deep, it led to the development of quantum mechanics. For now, astronomers are doubling down on observations. Next-generation observatories like the Square Kilometre Array, SKA, the European Extremely Large Telescope, ELT, and NASA's upcoming LYNX X-ray Observatory will allow even more detailed studies of these cosmic anomalies. Each new dataset brings us closer to understanding whether REX, J0335 and its kin are simply extreme outliers, or the first hints of new physics waiting to be discovered. The field of astrophysics is on the cusp of even more revolutionary discoveries. For decades, scientists have dreamed of instruments powerful enough to peer deeper into the cosmos and reveal its most closely guarded secrets. That dream is about to become reality. The next generation of telescopes, like NASA's Nancy Grace Roman Space Telescope and Europe's Extremely Large Telescope, promise to revolutionize our understanding of the universe. These cutting-edge observatories will possess unprecedented sensitivity, enabling them to detect and study the most extreme cosmic objects, including the so-called impossible black holes, with a level of detail we have never achieved before. The Roman telescope, often described as Hubble on steroids, will survey vast stretches of the sky, identifying thousands of quasars and early galaxies powered by ravenous black holes. Meanwhile, the extremely large telescope, with a mirror spanning a staggering 39 meters, will provide the resolving power to dissect those distant objects spectroscopically, teasing apart the chemistry, motions, and structures of their host galaxies. These instruments will not only confirm the existence of objects like Rex J032035, but will also map their growth histories, helping to answer the fundamental question of how they formed so quickly in the infant universe. Perhaps most exciting is the new frontier of gravitational wave astronomy. Unlike light, gravitational waves carry direct information about the motions of massive objects like black holes and neutron stars. Until recently, gravitational wave detection was limited to ground-based observatories like LIGO and Virgo, which can pick up the mergers of stellar mass black holes. But in the next decade, space-based detectors like the Laser Interferometer Space Antenna, or LISA, will extend this capability into entirely new territory. LISA will be sensitive to the mergers of supermassive black holes, titanic events that shape the growth of galaxies in the early universe. These signals will allow astrophysicists to directly measure the masses, spins, and growth patterns of black holes billions of years ago. Dr. Shaw McWills of West Virginia University, a leading voice in gravitational wave research, describes the promise vividly. Gravitational waves from early black hole mergers will give us a completely new window into the physics of the early universe. For the first time, we'll be able to watch the assembly of massive black holes in real time, even at epochs when the universe was less than 1 billion years old. It's like adding sound to a silent movie. Suddenly, the story of cosmic evolution comes alive. This isn't just about confirming theories. It's about transforming our entire approach to cosmic history. For the first time, astronomers will have both the light and the vibrations of space-time itself as tools to study the same objects. The implications for black hole physics are staggering. Yet beyond the technical challenges, the discovery of physics-defying black holes raises questions that stretch far beyond the boundaries of astrophysics. They force us to confront the very foundations of scientific knowledge. How confident can we be in laws that seem to break down in the most extreme corners of reality? If black holes can routinely exceed the Eddington limit, are those limits truly fundamental? Or are they merely approximations, useful in most cases but concealing deeper truths? Dr. Carlo Rowley, a theoretical physicist at IK Marseille's University and an authority on quantum gravity, reflects on this humbling possibility. The history of physics is full of moments when nature reminded us that our so-called fundamental laws were not as absolute as we believed. Newton's mechanics gave way to relativity. Classical physics gave way to quantum mechanics. The discovery of impossible black holes may be our generation's turning point, a sign that we are once again brushing up against the limits of human knowledge. The stakes are immense. The same physical laws that govern black holes underpin our models of the universe's fate, our calculations of planetary habitability, and even the theoretical blueprints for technologies humanity might one day build. If those laws prove incomplete, the consequences ripple outward, touching cosmology, astrobiology, and perhaps even the future of human civilization. Some researchers are beginning to see connections between black hole anomalies and other great mysteries of the universe, particularly dark energy. Dark energy is the invisible force driving the accelerating expansion of the cosmos, a phenomenon first confirmed in the late 1990s. Despite decades of research,
its true nature remains unknown. Intriguingly,
the energy scales involved in super-Eddington accretion are similar to those proposed for dark energy phenomena. If black holes can somehow tap into exotic physics involving vacuum energy or quantum fields, they might not only explain their own impossible growth rates, but also shed light on the mechanism behind cosmic acceleration itself. Dr. Adam Ree of Johns Hopkins University, a Nobel laureate for his role in discovering dark energy, highlights this tantalizing possibility. Any new physics that explains super-Eddington black hole growth could be directly relevant to dark energy. Both seem to involve processes at the boundary of our understanding, processes that deal with energy extraction from the fabric of space itself. It's possible that black holes are trying to tell us something profound about the engine that drives cosmic expansion. The week of September 2025 will likely be remembered as a turning point in science, not just for astrophysics, but for multiple disciplines at once. Breakthrough after breakthrough has forced humanity to reconsider its place in the cosmos. Interstellar visitors behaving in ways that defy physics, medical advances curing so-called incurable diseases with a single treatment, and black holes that seem to laugh in the face of our most trusted equations. Together, these discoveries represent more than isolated anomalies. They signal a broader shift. Nature is reminding us forcefully and repeatedly that the universe is far stranger and more complex than we dared to believe. For decades, some physicists predicted that we were nearing a theory of everything, a final unified framework that could describe all known phenomena. But Rex J03-35 and its kin stand as cosmic monuments to humility. The universe, it seems, still has many secrets left to reveal. As this chapter closes, another opens, one that shifts the spotlight from the depths of space to the planet right next door. Because while astrophysicists have been grappling with black holes that break the laws of physics, planetary scientists have delivered a discovery perhaps even more profound: evidence that life may once have existed on Mars. Chapter 5. We found life on Mars. Perseverance's smoking gun. For decades, the search for life on Mars has oscillated between hope and disappointment. Ambiguous findings have fueled endless debate, from the controversial Viking experiments of the 1970s to the Martian meteorite ALH-84 that captured headlines in the 1990s. Each time, skepticism ultimately prevailed, reminding us how difficult it is to distinguish biology from geology on an alien world. But now, in September 2025, that uncertainty may finally be over. NASA's Perseverance rover has uncovered what could be the strongest evidence yet that Mars once harbored life. And this time, the claim is not based on a single strange measurement or speculative interpretation. It comes from a carefully collected rock sample, scrutinized with multiple instruments, reviewed by dozens of scientists, and published in the pages of Nature. The evidence centers on a rock from an ancient riverbed, a place where water once flowed across Mars billions of years ago. The rock, nicknamed Chayava Falls by the science team, contained a distinctive pattern of dark spots surrounded by lighter halos, a leopard skin texture unlike anything seen on the red planet before. The rover's instruments reveal that these spots were not random mineral stains, but organized chemical structures rich in carbon, sulfur, and phosphorus, elements that, on Earth, are most commonly associated with microbial life. Dr. Joel Hurowitz of Stony Brook University, lead author of the landmark study, remembers the moment vividly. The instant we saw those spots, we knew we had stumbled upon something extraordinary. On Earth, patterns like this almost always mean biology, but we've learned from history to be cautious. That's why we subjected this rock to the most rigorous testing and analysis ever performed on Mars. The sample, now designated Sapphire Canyon, was drilled from the rock and stored in Perseverance's titanium tubes, awaiting possible return to Earth in a future sample return mission. But even before that day comes, Perseverance's onboard instruments, PXL and Sherlock, have delivered a wealth of data. PXL mapped the elemental composition at microscopic scales, while Sherlock identified complex organic compounds embedded within the rock. The results were stunning: a combination of organics, chemical patterns, and mineral structures that are extraordinarily difficult to explain through non-biological processes. Taken together, they represent the most compelling case yet for ancient Martian life. After decades of false starts, heartbreaks, and controversy, we may finally be on the verge of answering one of humanity's oldest questions. Are we alone? And if the answer is no, if even a single microbe once lived on Mars, then life may be far more common in the universe than we ever dared to dream. The discovery of vivianite and greigite in the Martian rock sample from Sapphire Canyon has turned into one of the most exciting and consequential findings in planetary science. These minerals are not just random chemical curiosities. They represent a kind of chemical fingerprint that scientists associate with biological activity on Earth. Their presence, along with the precise and organized way they are distributed within the rock, provides one of the strongest potential pieces of evidence for past microbial life ever discovered on Mars. Vivianite is an iron phosphate mineral that typically forms in low-oxygen environments where organic matter is decaying. On Earth, it is commonly found in bogs, wetlands, lakebed sediments, and areas where plant and animal material has been slowly decomposing over long periods. Its formation requires specific chemical conditions, especially reducing conditions, in which oxygen is being actively consumed, conditions that are most easily achieved when microorganisms are breaking down organic material and altering the surrounding chemistry. Finding vivianite in a Martian riverbed suggests that similar processes may have taken place there billions of years ago. Greigite, the other mineral found in the sample, is perhaps even more compelling. Greigite is an iron sulfide mineral that is known to form as a result of microbial metabolism, particularly the activity of sulfate-reducing bacteria. These ancient microorganisms use sulfate compounds as an energy source, producing hydrogen sulfide as a byproduct. On Earth, they thrive in extreme oxygen-poor environments such as hydrothermal vents and deep-sea sediments, places that may resemble ancient Martian habitats. The fact that both vivianite and greigite were found together, arranged in a very particular pattern, makes the discovery especially significant. Dr. Michael Ty of Texas A&M University, a co-author of the landmark study, explained it this way: finding vivianite and greigite together in this pattern is like discovering a fossilized fingerprint of life. On Earth, when we see this mineral combination with this exact spatial arrangement, it almost always indicates biological involvement. But the minerals themselves are only part of the story. Equally crucial is how they are distributed. Throughout the rock, the so-called leopard spots that first caught the science team's attention turned out to be precisely organized zones where these iron-bearing minerals had concentrated during the rock's formation. Using Pixel, Perseverance's high-resolution X-ray fluorescence spectrometer, the team discovered that each spot was not random, but instead formed a concentric ring pattern. Vivianite-rich zones at the center, surrounded by greigite-rich halos. Geologists call these features reaction fronts, boundaries where chemical gradients were actively shaping mineral formation. This type of pattern is exactly what would be expected if organic material was decomposing in place, changing the local chemical environment over time. The process works like this. When microbes die, their remains create pockets of chemically active material. The decomposition process consumes oxygen, creating localized reducing conditions that favor the formation of vivianite. If sulfate-reducing microbes were present, they would have produced hydrogen sulfide, which then reacted with iron in the sediment to form greigite. Over time, this leads to a bullseye-like distribution of minerals, a chemical fossil of biological activity. The fact that Chayava Falls shows this precise pattern is extremely difficult to explain through purely geological means. Dr. Abigail Wood of NASA's Jet Propulsion Laboratory, one of the foremost experts on biosignatures, described these features as fossil chemical ecosystems. In her words, they preserve the spatial relationships between different biological processes that were happening billions of years ago. It's as close as we can currently get to directly seeing an ancient Martian microbial community, but perhaps the most compelling piece of evidence is the discovery that the highest concentrations of organic carbon were found in exactly the same locations as the mineral-rich spots. Sherlock Perseverance's laser spectrometer detected what scientists call the G-band signal, a specific spectroscopic fingerprint associated with complex organic carbon, at the site the team nicknamed Apollo Temple, where both vivianite and greigite were most abundant. This co-location is unlikely to be coincidental. Instead, it suggests that the organic matter was not only present but actively involved in driving the chemical reactions that created the minerals in the first place. And these are not just simple carbon molecules that could have been formed abiotically, such as methane or carbon monoxide. The molecules Sherlock detected are chemically complex, resembling the building blocks of life: lipids, amino acid precursors, and fragments of proteins. Dr. Luther Beagle, the principal investigator for Sherlock, emphasized this point. We're not just seeing random organic carbon, we're seeing organic compounds with complexity and chemical signatures we associate with biology on Earth. This is the kind of chemistry you'd expect from living systems. After making these extraordinary discoveries, the science team faced an even more daunting challenge: convincing the global scientific community. They knew that any claim hinting at life on Mars would face intense scrutiny and possible skepticism, so they prepared for the most rigorous peer review process possible. Their findings were submitted to Nature, one of the world's most prestigious scientific journals, in early 2024. What followed was over a year of meticulous review by independent experts in planetary science, geochemistry, and astrobiology. The reviewers challenged every assumption, demanding alternative explanations. Could the minerals have formed through high-temperature hydrothermal processes unrelated to life? Could unusual water chemistry create these patterns abiotically? Could meteorites have delivered the organics from space? The team systematically tested each of these possibilities and demonstrated that none could fully account for the observed combination of minerals, organics, and spatial patterns. The rock shows no signs of exposure to high temperatures that would be needed for abiotic mineral formation, and the specific organic molecules present are inconsistent with simple meteoritic contamination. After a year of intense back and forth, the paper was accepted and published in September 2025, a milestone that gives the findings an enormous boost in credibility. Dr. David Flannery of Queensland University of Technology, who was not involved in the study, praised the work as one of the most thorough and cautious analyses ever conducted in Mars science. He added, "While we can never completely rule out some exotic abiotic process, the biological interpretation remains the simplest, most parsimonious explanation for all of the data. The geological context of the discovery only strengthens its importance. Neretva Vallis, where Chayava Falls is located, is one of the most promising paleo-environmental sites on Mars. About 3.7 billion years ago, it was part of a river system that fed a large lake in Jezero Crater, a lake that persisted for millions of years. These conditions, standing water, stable climate, abundant chemical energy, make this one of the most Earth-like environments ever identified on Mars. The sediments that Perseverance drilled into are mudstones and conglomerates deposited during this habitable period, preserving a record of environmental conditions during Mars's transition from a warmer, wetter world to the cold desert it is today. Even more remarkable is the timing. The Sapphire Canyon sample dates to about 3.7 billion years ago, exactly the same period when life was thriving on early Earth. Our planet at that time was dominated by microbial life forms living in hot springs, riverbeds, and shallow lakes, environments nearly identical to those in Jezero Crater. The chemical and mineral signatures in the Martian rock are strikingly similar to those found in Earth rocks of the same age that are known to contain fossilized microbial mats. The parallel suggests that if life arose on Earth, it may well have arisen on Mars as well. Astrobiologists use a tool called the Confidence of Life Detection (CoLD) scale to rate potential evidence of extraterrestrial life. This 7-step scale ranges from level 1, a simple detection of potentially interesting patterns, to level 7, a confirmed detection of life with independent verification. The Sapphire Canyon findings currently sit at about level 4, classified as a potential biosignature with compelling supporting context. Moving to level 5 or higher would require additional lines of evidence, potentially including direct imaging of microfossil structures or isotopic analysis showing patterns that can only be produced by biological processes. And this is why the sample return mission is so critical. The core from Sapphire Canyon is currently stored in a sealed titanium tube aboard Perseverance, waiting for retrieval. NASA and ESA's Mars Sample Return mission aims to bring it back to Earth in the early 2030s. Once here, scientists will be able to analyze it with laboratory instruments thousands of times more sensitive than anything Perseverance carries. They could perform isotopic studies to look for biological fractionation, use electron microscopes to search for microfossils, and conduct detailed chemical analysis to confirm the biological origin of the organics. Dr. Meenakshi Wadhwa, lead scientist for Mars Sample Return, put it simply: bringing this sample back to Earth could finally answer the question of whether we are alone. If the results hold up, Sapphire Canyon could become one of the most historically significant rock samples ever studied, our first direct evidence that life existed beyond Earth. For now, the discovery offers something humanity has sought for decades, not just speculation, but scientifically rigorous hope that we are not alone in the universe. The search for life on Mars has always been one of humanity's most ambitious scientific quests, and the discovery of the intriguing mineral and organic signatures at Sapphire Canyon has brought that quest to a turning point. We now stand at the edge of a potential breakthrough that could confirm once and for all whether Mars was ever a living world. The evidence collected by NASA's Perseverance rover points strongly toward the presence of complex organics and mineral structures that, on Earth, are often associated with biological processes. But a discovery of this magnitude demands not just excitement, but absolute certainty. And certainty can only come from bringing the samples back to Earth for deeper analysis. The Mars Sample Return Program was designed to answer exactly this kind of question. Perseverance has carefully drilled and sealed a set of core samples, including the critical specimen from Sapphire Canyon, which could hold the key to determining whether these features represent the remains of ancient life or some as yet unrecognized geological process. However, returning those samples to Earth is no simple task. The mission is one of the most technically complex endeavors ever attempted in space exploration. It involves launching a rocket from the Martian surface, rendezvousing with an orbiter, and returning the sealed samples to Earth, all without contamination. It is a mission that will cost billions of dollars and require international collaboration. Unfortunately, that ambitious plan now faces growing uncertainty. The Mars Sample Return mission has already experienced significant delays and escalating costs. The current timeline estimates the samples could be back on Earth in the early 2030s, but that date has been pushed back more than once, and even NASA admits it is not set in stone. Budgetary pressures are mounting, and the mission's future is under threat. This has not gone unnoticed at the highest levels of government. In a recent press briefing, acting NASA Administrator Shaw Duffy underscored the magnitude of what Perseverance had accomplished. This finding by Perseverance, launched under President Trump during his first term, is the closest we have ever come to discovering life on Mars, Duffy said. The identification of a potential biosignature on the red planet is a groundbreaking discovery, one that could fundamentally advance our understanding of Mars and of life itself. Yet even as NASA celebrates its success, the political winds are shifting. The proposed 2026 federal budget calls for major cuts to planetary science, including the possible termination of the Mars Sample Return Program itself. The timing is almost painfully ironic. Just as humanity may have stumbled across its most convincing evidence for ancient extraterrestrial life, the very program needed to confirm that discovery faces the possibility of being canceled. Duffy tried to strike a hopeful tone, telling reporters, "We believe there's a better way to do this, a faster way to get these samples back. Can we do it faster? Can we do it cheaper? And we think we can." But so far, NASA has not shared specific details about what that alternative plan might look like, leaving many scientists anxious that cost-cutting could come at the expense of scientific rigor or even mission success. Another crucial question surrounds the issue of contamination. One of the most important tasks for scientists is proving that the organic material found at Sapphire Canyon truly originated on Mars and is not the result of accidental contamination from Earth. This has been a major challenge in astrobiology for decades. Several past claims of Martian life, including the famous ALH 84001 meteorite controversy, were eventually dismissed after contamination or abiotic processes were found to be more likely explanations. Perseverance was designed from the beginning with this problem in mind. Every part of its sampling system was rigorously sterilized before launch, and the rover carries control samples to help scientists identify any contamination that might have been introduced during assembly or landing. More importantly, the specific types of organics detected in the Sapphire Canyon sample do not match the types of chemicals typically used in spacecraft construction or cleaning. Instead, they display chemical signatures far more consistent with ancient biological processes. Dr. Andrew Steele of the Carnegie Institution for Science, one of the world's leading experts on planetary contamination control, explained, "The contamination controls and chemical signatures strongly suggest that the organic compounds detected in Sapphire Canyon are indigenous to Mars. This gives us confidence that we're seeing genuine Martian biosignatures, rather than terrestrial contamination, if Steele and his colleagues are correct. The implications are nothing short of revolutionary. The potential discovery of ancient life on Mars could transform not just planetary science, but our entire understanding of biology and the universe. For all of human history, Earth has been the only known cradle of life. If life arose independently on Mars, it would mean that life is not a rare cosmic accident, but perhaps a common consequence of the right environmental conditions. Dr. Sarah Seeger of MIT, one of the world's most respected astrobiologists, has described the potential breakthrough as one of the most important discoveries in human history. She explains, "If we can confirm that these signatures represent ancient life, it tells us that the origin of life is not an impossible event. It is something that can happen on multiple worlds. That means life could exist throughout the galaxy, perhaps even throughout the universe, wherever conditions are suitable." This discovery would also represent the culmination of decades of work. Since the Viking missions of the 1970s, scientists have dreamed of finding definitive evidence of life on Mars. Vikings' biology experiments produced ambiguous results that left the question unresolved, but they ignited a half-century of exploration that has now brought us to this moment. The discovery at Sapphire Canyon suggests that this long scientific quest may finally be nearing success. Beyond science, the implications are profoundly philosophical. For thousands of years, humanity has asked the question, are we alone? Confirmation of even the simplest microbial life on Mars would mean the answer is no. It would mean that our solar system has hosted at least two independent origins of life. This, in turn, would make it almost certain that life exists elsewhere in the cosmos. Dr. David Grinspoon, an astrobiologist at the Planetary Science Institute, reflected on the potential meaning. The discovery of life on Mars, even ancient, microscopic life, would change how we see ourselves. We would no longer be a solitary accident in a lifeless universe. We would be part of a much larger story, part of a living cosmos. The discovery also intensifies the urgency for continued exploration. Perseverance has already collected 30 samples, with several more still under consideration. Many of these cores contain rocks from different geological layers, each offering a window into a different era of Martian history. The rover continues to explore Jezero Crater, searching for additional sites that might yield even more promising evidence. Other missions are also on the horizon. The European Space Agency's Rosalind Franklin rover, part of the ExoMars program, will carry a drill capable of reaching up to 2 meters below the surface, potentially accessing materials that have been shielded from radiation for billions of years and may be even better preserved than surface rocks. Future missions may include specialized instruments designed to look directly for microfossils or to measure isotopic ratios that could definitively distinguish biological from non-biological processes. But time is not unlimited. Mars and Earth align favorably for mission launches only once every 26 months, limiting opportunities for new exploration. Budget constraints, political battles, and shifting national priorities threaten to delay or cancel planned missions. Perseverance itself will not last forever. Its nuclear power source will gradually weaken, and the rover's systems will eventually fail. Each sample it collects is precious, and each day that passes brings us closer to the end of its operational life. This sense of urgency has sparked intense public and global interest. Social media has lit up with discussions about what the discovery means for the future of space exploration. Educators are using the news to inspire the next generation of scientists and engineers. International space agencies have taken notice as well. China, which has already landed its own rover on Mars, may accelerate its plans for a sample return mission. The European Space Agency is likely to use the discovery as additional justification for its own missions. The Sapphire Canyon finding may mark the beginning of a new era of global collaboration or competition, focused on answering the most profound question humanity has ever asked. As we stand at this threshold, one thing is clear: the Sapphire Canyon discovery is both an ending and a beginning. It may mark the end of our cosmic loneliness and the beginning of a new understanding of life as a universal phenomenon. Whether through NASA's Sample Return Program, international collaboration, or future robotic explorers, the quest to confirm Martian life will continue. And if the evidence holds, it will be remembered as the moment when humanity truly began to see itself not as an isolated species on a small blue planet, but as part of a vast and living universe. But as the narrative of September 2025 continues, it becomes clear that the theme of impossible discoveries does not end with Mars. If anything, the revelations taking place back on Earth are even stranger, blurring the line between cutting-edge physics and science fiction. While Perseverance is unearthing possible signs of ancient microbial life on the red planet, physicists here on Earth have stumbled onto something that could change not just how we see the cosmos, but how we interact with it. The breakthrough came in one of the most unlikely places: superconducting materials, the very building blocks of many quantum circuits. Researchers were not looking for a revolution. They were performing what they thought was routine spectroscopy on these materials, probing their quantum behavior to better understand the fleeting collective vibrations of their electron pairs. What they found instead has been described as quantum echoes from another dimension, mysterious signals that seem to defy conventional quantum theory and could open entirely new pathways for computing, information storage, and perhaps even our understanding of reality itself. This discovery is not merely another incremental advance in quantum science. It is a paradigm-shifting event that is forcing physicists to reconsider their most fundamental assumptions about the behavior of matter at its smallest scales. The signals being observed, what researchers are calling Higgs echoes, are so strange that they almost seem to remember the past, storing information in ways that should not be possible according to our current understanding of physics. If confirmed, this finding could lead to quantum computing systems with memory retention and stability orders of magnitude beyond anything that exists today, rendering even the fastest supercomputers of 2025 obsolete. The superconducting frontier to appreciate the magnitude of this discovery. It helps to understand what makes superconductors unique. These materials are sometimes called perfect conductors because, when cooled to extremely low temperatures, they can carry electric current with absolutely zero resistance. That means no heat loss, no wasted energy, and effectively infinite conductivity. In practical terms, superconductors are like frictionless highways for electricity, perfectly efficient systems that seem to cheat the normal rules of thermodynamics. But superconductors are far more than just efficient wires. They are quantum laboratories where the everyday rules of matter give way to phenomena so exotic they defy classical intuition. When a material becomes superconducting, its electrons stop behaving like individual particles and instead form Cooper pairs, pairs of electrons that act as a single quantum entity, moving in perfect synchronization across macroscopic distances. This collective behavior creates a macroscopic quantum state, meaning the entire material behaves like one unified quantum object. Within these superconducting states exist what are called Higgs modes, subtle quantum vibrations of the electron pairs that maintain the superconducting order. The name Higgs mode is borrowed from the famous Higgs boson, the particle associated with the Higgs field that gives matter its mass. But in this context, it describes a different kind of collective oscillation. These modes have fascinated theorists for decades because they represent a window into the hidden symmetries of quantum materials. The problem is that Higgs modes are notoriously ephemeral. They typically exist for only a few billionths of a second before dissipating into what physicists call quantum noise. They are like ghosts, present for the briefest of moments and then gone. This fragility has made them exciting to theorists but frustrating to experimentalists, who until now have had little hope of harnessing them for practical applications. The echo effect that shouldn't exist. Everything changed when Dr. Jigang Wang of the U.S. Department of Energy's Ames National Laboratory and his team set out to study these Higgs modes using terahertz spectroscopy, a cutting-edge technique that uses pulses of extremely high-frequency electromagnetic radiation to probe quantum materials. The team was working with niobium-based superconductors, which are widely used in quantum computing circuits, when they noticed something strange. They expected to see the usual brief flash of Higgs activity that quickly decays. Instead, they began detecting secondary signals, echoes, that appeared long after the original mode should have vanished. At first, they suspected an experimental error or instrument malfunction. But repeated tests ruled out those explanations. What they were seeing was real Higgs modes that were somehow reappearing, as if the quantum system was replaying its own past. Dr. Huang, the lead author of the study later published in Science Advances, recalled the team's initial shock. We kept seeing these secondary signals that appeared to be related to the original Higgs modes, but were occurring at completely different times. At first, we thought it was a calibration problem or noise from the equipment, but as the data piled up, it became clear that we were witnessing a completely new quantum phenomenon. Unlike acoustic echoes, where sound waves bounce off a wall and return to the listener, these were purely quantum echoes. Interference patterns formed when Higgs modes interacted with other quantum excitations in the superconductor known as quasi-particles. Quasi-particles are one of the strangest concepts in modern physics. They are not particles in the classical sense, but collective excitations of the system that behave as if they were independent entities. In a superconductor, quasi-particles represent tiny cracks in the perfect coherence of the superconducting state. What Wang's team discovered was that these Higgs modes and quasi-particles could interact in just the right way to create a kind of quantum memory effect. The system was not simply decaying into randomness, it was holding on to information and then reproducing it later in a measurable way. The quantum memory effect. This is where the story becomes truly revolutionary. By carefully tuning the timing and intensity of their terahertz pulses, the researchers found they could encode specific patterns of information into these quantum echoes. Even more astonishing, they were able to retrieve this information hours, and in some cases days, after the initial encoding, something previously thought impossible in such fragile quantum systems. Dr. Martin Moots, a co-author of the study, explained the implications. We are essentially seeing quantum memory at work. The superconductor is storing information in a form that persists far longer than we thought possible. This discovery could fundamentally change the way we think about quantum information storage and processing. One of the greatest challenges in quantum computing is decoherence, the tendency of quantum states to collapse into classical states when disturbed by even the slightest environmental noise. Decoherence forces quantum computers to perform their calculations incredibly quickly before the information degrades, which severely limits their performance and scalability. If the Higgs echo effect can be harnessed, it could provide a mechanism for building quantum systems with far more robust memory, systems that can hold quantum information stable long enough to perform far more complex computations. Some researchers are even speculating that this phenomenon could pave the way for entirely new forms of quantum error correction, eliminating one of the biggest obstacles standing in the way of practical, large-scale quantum computers. The result could be machines capable of simulating molecular interactions with perfect precision, solving optimization problems beyond the reach of classical computers, and perhaps even modeling the quantum fabric of spacetime itself. Beyond technology, a window into reality. The implications of the Higgs echo discovery go far beyond technology. If these quantum echoes are real, and multiple laboratories are now racing to replicate the results, they could provide a new way of probing the deepest layers of physical reality. Some theorists have suggested that the echoes may represent interactions between different quantum vacua, potentially offering clues about how quantum fields evolve and interact across scales. Others have proposed even more radical ideas, suggesting that the echoes could hint at hidden dimensions of reality or deeper symmetries that we have not yet discovered. Dr. Wang himself has been cautious but optimistic, saying, "Every time physics has shown us a phenomenon that seems to break our rules, it has eventually led to a deeper and more unified understanding of the universe." This breakthrough arrives at a moment when multiple fields of science are being shaken by discoveries that challenge long-standing assumptions, from black holes that defy the Eddington limit, to interstellar objects behaving in ways that seem almost engineered, to possible biosignatures on Mars. September 2025 is becoming a month that will be remembered as a turning point in human understanding. The Higgs echo discovery may prove to be one of the most consequential of them all, ushering in a new era of quantum science that could change not just our technology, but our very concept of reality. While physicists are uncovering quantum echoes that preserve information in superconductors, computer scientists and behavioral researchers have made a discovery that feels equally extraordinary, and perhaps even more unsettling. They have learned how to turn the device sitting in your pocket or resting on your bedside table into a window into your psychological state. Your smartphone, the same device you use to text friends, watch videos, scroll through news feeds, and set alarms, may now be capable of detecting your mental health status with surprising accuracy. This breakthrough is not science fiction. It is a growing field of research known as digital phenotyping, the use of passive data collection from smartphones and wearables to infer a person's cognitive, emotional, and behavioral state. Researchers are no longer asking you to fill out questionnaires, report your mood, or schedule expensive therapy sessions just to determine if you might be suffering from depression, anxiety, ADHD, PTSD, or even early signs of neurological disorders. Instead, they are analyzing patterns hidden within the way you tap your screen, how quickly you respond to notifications, how often you unlock your device, how much you move during the day, and even the tone and rhythm of your speech during voice messages. The results have been astonishing. Machine learning models trained on this behavioral data can detect signs of mental health disorders, with accuracy rates approaching or even surpassing those of traditional clinical assessments. In some studies, algorithms have been able to predict depressive episodes weeks before a patient reports symptoms, offering the possibility of early intervention that could save lives. Imagine a system where your phone could warn you, or your doctor, that you are on the verge of a major depressive episode, allowing you to seek help before you spiral into crisis. But this powerful capability comes with a cost. If a phone can infer your mental state, it also means that someone, whether researchers, app developers, or corporations, could access the most intimate details of your emotional life without your explicit consent. For the first time in history, technology has made it possible to create a continuous psychological profile of billions of people, passively and invisibly, in real time. The science behind digital mind reading. The foundation of this new capability lies in what researchers call passive sensing. Modern smartphones are equipped with a vast array of sensors, accelerometers, gyroscopes, GPS receivers, microphones, proximity sensors, light detectors, and of course, detailed logs of every tap, swipe, and scroll. Each of these generates streams of data, most of which are never directly seen by the user. By itself, a single data point might seem meaningless. The number of times you unlock your phone today doesn't say much about your mental state, but combine thousands of such signals, the time of day you are most active, the speed of your typing, the amount of time you spend on certain apps, the variation in your speech patterns, and you get a remarkably detailed picture of your daily rhythms. Machine learning algorithms excel at detecting patterns that are too subtle or complex for humans to recognize. For example, a slightly slower typing speed combined with fewer text messages sent per day might indicate fatigue or low mood. A drop in mobility, detected through GPS data, could suggest social withdrawal, one of the key behavioral markers of depression. Even something as simple as how steadily you hold your phone can be correlated with neurological or anxiety-related conditions. The field has advanced so rapidly that researchers are now exploring how to differentiate between multiple conditions based on digital biomarkers. One study demonstrated that it was possible to distinguish between depression and anxiety disorders based purely on phone usage patterns. Another experiment used speech analysis to predict manic episodes in patients with bipolar disorder days before they occurred. These insights suggest a future in which mental health monitoring is as continuous and unobtrusive as tracking your steps or heart rate on a fitness app. Benefits: early intervention and continuous care. The potential benefits of this technology are profound. Mental health conditions often go undiagnosed for years, partly because of stigma, limited access to care, and the episodic nature of psychological symptoms. Many people seek help only after their condition has significantly worsened, which makes treatment more difficult and recovery longer. Imagine if your smartphone could serve as an always-on mental health companion, alerting you and your care provider to subtle changes in mood, sleep patterns, and cognitive performance. Early intervention is one of the most effective strategies in mental health treatment, and digital phenotyping could allow for intervention at the earliest possible stage, perhaps even before symptoms become consciously noticeable. For individuals with chronic conditions, such as PTSD or schizophrenia, continuous monitoring could help prevent relapses. If the system detects that a patient is showing early warning signs, reduced social interaction, changes in movement patterns, irregular sleep, it could prompt them to schedule an appointment, adjust medication, or engage in therapeutic exercises before the situation escalates. This technology could also be a powerful tool for suicide prevention. Researchers have already demonstrated that algorithms can detect elevated suicide risk based on phone usage data. In theory, a phone could issue an emergency alert to friends, family, or health professionals if it detects a pattern associated with severe crisis, potentially saving lives. The privacy dilemma. Yet for all its potential, the technology raises urgent ethical and privacy concerns. Your phone may soon know more about your mental state than you do. But who else gets to know? Right now, most research is being conducted under strict ethical guidelines, with informed consent from participants. But what happens when this technology moves from the lab to the consumer marketplace? Will app developers quietly build mental health detection into their platforms? Could advertisers use psychological profiling to target people when they are most vulnerable, for example, delivering ads for food delivery, when your phone detects loneliness, or for payday loans when you're stressed about finances? Even well-intentioned uses could become problematic. Imagine an employer gaining access to your mental health profile and using it to make decisions about hiring, promotions, or layoffs, or insurance companies adjusting your premiums based on your risk of developing depression or addiction. Privacy advocates argue that we need robust legal frameworks to regulate the use of digital phenotyping data before it becomes another commodity traded in the surveillance economy. The stakes are higher here than with ordinary location or browsing data because mental health information is among the most sensitive data a person can have. Algorithmic bias and ethical risks another. Challenge is the potential for bias in these AI models. If the training data is skewed towards certain populations, the system may misinterpret signals from others, leading to false positives or negatives. A model trained mostly on data from young urban smartphone users, for instance, might not perform well for older adults, rural populations, or people with different cultural patterns of communication. False positives could lead to unnecessary interventions, stigmatization, or anxiety. False negatives could delay much-needed help. To avoid harm, researchers emphasize the need for transparent algorithms, careful validation across diverse populations, and human oversight in any system that delivers mental health assessments. The coming era of ambient mental health monitoring. Despite these concerns, the momentum behind this technology is growing. Major tech companies are already exploring ways to integrate mental health monitoring into operating systems and wearable devices. Apple has introduced features that use passive data to estimate mood trends. Google and Samsung have partnered with universities to study mental health through smartphone usage. Even social media platforms are experimenting with ways to detect signs of psychological crisis and intervene. It's likely that within the next decade, ambient mental health monitoring will become a standard feature of personal technology. The question is not whether it will happen, but under what conditions, and who will control the data. A new relationship with technology, if done responsibly. This technology could fundamentally change the way we think about mental health. Instead of reactive care that begins after a person reaches a breaking point, we could move toward a model of continuous, preventive mental health maintenance. Your phone could become not just a source of distraction or stress, but an active participant in your psychological well-being. A kind of always-present therapist that quietly keeps watch, ready to intervene when needed. But such a future will require more than technical innovation. It will require public trust, robust privacy protections, clear consent mechanisms, and careful attention to the risks of algorithmic decision-making. We will have to decide whether we are comfortable living in a world where the device in our pocket can sense our sadness before we do, and where that information might be stored, shared, or monetized. What is certain is that the boundary between our digital lives and our inner lives is rapidly dissolving. Just as quantum echoes are revealing hidden pathways in the fabric of reality, smartphones are revealing hidden pathways in our minds. The convergence of neuroscience, AI, and ubiquitous sensing promises to transform mental health care and perhaps our understanding of what it means to be human in ways that we are only beginning to grasp. The most unsettling truth about this technology is that it isn't some distant, futuristic innovation. It is happening right now, using data that your smartphone is already collecting every second of every day. What most of us think of as a convenient communication tool is, in reality, an incredibly sophisticated network of sensors constantly monitoring our behavior. Your smartphone is not just a phone. It is, as researchers like to put it, a sensor laboratory disguised as a device for calls and messages. Hidden within that familiar rectangle are accelerometers that measure your movements, gyroscopes that detect rotation, GPS receivers that log your location, microphones that capture audio, cameras that record images and video, and touchscreens that silently measure every tap, swipe, and gesture. Most people understand the obvious uses of this data. GPS makes navigation possible, accelerometers allow your screen to rotate when you tilt the device, and microphones let you talk during calls. But what almost no one realizes is that these sensors are always on, collecting and storing information even when you aren't actively using them, creating a continuous, high-resolution digital fingerprint of your life. This fingerprint includes where you go, how fast you walk, how you use your apps, how long you stay in bed after waking up, how hard you tap your screen, how frequently you pick up your device, and even patterns in how you scroll or type. Dr. Colin Weiss of the University of Pittsburgh, who co-led one of the most groundbreaking studies in this field, put it bluntly, your phone knows when you wake up, how long you stay in bed, where you go, who you call, how long you spend staring at the screen, and thousands of other behavioral markers. In other words, your smartphone is compiling a psychological profile of you that is far richer and more continuous than any traditional clinical assessment. What makes this development so revolutionary is that this data is gathered passively. You do not need to fill out surveys, record your mood manually, or even be aware that this tracking is happening. The system simply observes your natural behavior in real time and builds a detailed portrait of your mental state based on subtle patterns that are often invisible to human perception. The research, published in JAMA Network Open after a rigorous peer review process, represents the first large-scale demonstration that passively collected smartphone data can be used to reliably identify symptoms of mental health conditions across a broad spectrum: depression, anxiety, ADHD, and more. The key insight is that mental health does not just change how people feel, but also how they behave in quantifiable ways. For example, people with depression often experience disrupted sleep cycles, reduced physical activity, and social withdrawal, patterns that show up in accelerometer and GPS data long before they might show up in conversation. Anxiety may manifest as restlessness, faster walking, irregular movement patterns, and changes in communication frequency. ADHD often reveals itself through short attention spans, frequent app switching, and inconsistent task completion. These behavioral traces may look like noise to the casual observer but can be clearly identified by sophisticated AI models trained to detect them. Dr. Whitney Ringwald, lead author of the study and now a professor at the University of Minnesota, explained that these behavioral signatures are surprisingly consistent. We found that people with similar mental health symptoms show remarkably similar patterns in their smartphone usage, even when they come from completely different backgrounds and live completely different lives. The digital signatures of psychological distress are apparently universal. Researchers combined this digital data with comprehensive clinical assessments, then trained machine learning models to identify which patterns were most predictive of specific conditions. Some results were expected, such as depressed participants being less physically active and spending more time at home, but others were startling. People with anxiety, for example, tended to tap harder on touchscreens and scroll more erratically on social media. Those with ADHD frequently abandoned tasks midway and bounced between applications rapidly. Participants with narcissistic personality traits spent significantly more time taking and editing selfies. The breakthrough was made possible by advances in machine learning that can process enormous volumes of high-dimensional behavioral data. Unlike traditional statistical methods, which require researchers to guess which variables might be relevant and test them one by one, machine learning algorithms can analyze thousands of metrics simultaneously, discovering subtle patterns that no human could detect manually. Dr. Aidan Wright of the University of Michigan, one of the pioneers behind these analytical techniques, described it this way: "We're essentially teaching computers to recognize the digital signatures of different mental health conditions by showing them thousands of examples of how people with those conditions behave. The algorithms learn to spot patterns that are far too complex and subtle for human observers to detect." The results were astonishing. For conditions like major depressive disorder and generalized anxiety disorder, the algorithms achieved accuracy rates above 80%, based solely on smartphone data. In some cases, the models could detect early warning signs of psychological distress, days or even weeks before the individual noticed anything was wrong. This predictive power is perhaps the most transformative aspect of the technology. Mental health crises rarely happen overnight. They build up gradually, leaving faint but detectable behavioral markers along the way. For example, the gradual decline in physical activity and reduced social interactions that often precede a depressive episode can be picked up by a smartphone long before emotional symptoms become overwhelming. Graduate researcher Grant King, who worked on the predictive modeling, summarized it well. Mental health crises don't just appear out of nowhere. They develop over time, and that development process leaves clear signatures in smartphone data. If we can detect those signatures early enough, we have a chance to intervene before the crisis hits its peak. Imagine a future in which a smartphone can detect the early onset of a manic episode in someone with bipolar disorder and automatically alert their doctor, or an app that notices a pattern associated with suicidal ideation and immediately connects the person with crisis intervention resources. This could fundamentally shift mental health care from being reactive to being proactive, catching problems early and preventing suffering before it escalates. But with this power comes a serious privacy dilemma. The same data that makes early intervention possible could also be used for surveillance, discrimination, and manipulation. This technology effectively turns every smartphone into a psychological monitoring device, capable of revealing intimate details about its user, details that even close friends or family might not know. Location history, communication patterns, sleep cycles, and interaction data are extremely sensitive. Employers could theoretically use this data to screen job applicants for mental health risk. Insurance companies could adjust premiums based on predicted psychological vulnerability. Governments or law enforcement could use it for profiling or risk assessments. Dr. Weiss warned, "There's enormous potential for misuse of this technology." We're talking about algorithms that can detect psychological vulnerabilities that people might not even be aware of. In the wrong hands, this could lead to entirely new forms of discrimination and manipulation. Most users have already agreed to terms of service that allow their data to be collected, often without fully realizing the scope of what they've consented to. And because mental health applications of this data weren't envisioned when most privacy regulations were written, there are few legal protections in place to prevent abuse. On the other hand, the potential clinical benefits remain extraordinary. Mental health care has always relied heavily on self-reporting, which is often unreliable. Patients forget, minimize, or misinterpret their own symptoms. Passive smartphone monitoring could provide clinicians with continuous, objective data, giving them a far clearer picture of what's happening between appointments. As Dr. Jessica Schleider of Stony Brook University put it, this technology could give us an unprecedented window into the real-world experiences of people with mental health conditions. We could see how symptoms evolve over time, how they respond to treatment, and how external events impact them, all in ways we could never measure before.